everyone. My name is Aubrey Komorski, and I'm the project manager and the second structural engineer with Jake Engineering. With me today, I have Kenzie Green, our transportation engineer, Emil Friesvillen, our other structural engineer, and Jonathan Bone, our water resources engineer. Today, we will be presenting on our progress on Eastgate development and our design of a road connecting Silhavy and Sturdy roads, along with a parking lot that will accommodate 2 buildings and the treatment of runoff that will be performed by our water resources engineer and a design of a culvert. Now I will pass it on to Kenzie.
Hello everybody. As Aubrey said, my name is Kenzie Khan and I am the transportation engineer for Jake Engineering. The scope of my project is to design a new roadway from Silhavy to Sturdy with an improvement of the 2 intersections and then improvement to the pedestrian facilities. So as you can see here, this is my detour route. For here, Sturdy Road will be closed due to the intersection improvement of the new signal. And then I have a main detour, which is for smaller cars, but I'm guessing the trucks will not be able to make this curve right here due to the narrow and that. So I created a truck detour to go around, which is about a 5-minute longer detour, but it will create more access for them. So this is my new road alignment. As you can see, I have 2 500-foot curve radii, and then it has a connection to the Sturdy Road intersection and the Silhavy Road intersection. This will be a signal, and that will be a one-way stop. Here is my typical section of the roadway. As you can see, it is a 2% typical slope with a 5-foot concrete sidewalk on the right, which will be on the south side of the road, with a 15-foot ditch on each side of it. And then down here you can see the cross area of the local road collector road parking lot due to the different types of things, because the difference is the base and the aggregate, just because local roads don't take as much as a collector road, which would be Sturdy Road, just because it's a major road instead of a minor road. And then here is my alignment for my new roadway. The main point of this is the culvert right here that you will hear more from our water resources. And then here is my parking lot, which will be connected to my new roadway. It will be designed for 217 20x9 spaces, 5 20x9 handicap parking spots with a 20x5 access aisle, and then 2 20x11 van parking spaces with also a 20x5 access aisles, 2 bike racks, and 1 loading zone. This was all designed to Valparaiso city standards, and then there will also be a sidewalk to the entrance of our 2 buildings. And then this is a more in-depth of the dimensions on my parking lot. As you can see, the 20x9 parking spots, and then these vary depending on how much extra room was used. And then here are my 2 intersections. On the left, we have the Sturdy Road intersection, which has 300-foot radii for the curves, and then an 8-foot crosswalk, 12-foot lanes, which is all designed to the City of Valparaiso standards. Similarly, the Silhavy Road also has 12-foot lanes with 300-foot radii, and then here you can see this will be the new design of a concrete sidewalk, and then these will just be markings on the road. So for future work, I will finalize the alignment, intersections, and parking lot, and then I'll be working with the water resources to integrate a culvert into our transportation design. And now you'll hear from our first structural engineer, Emil.
As mentioned, I am one of the structural engineers, and I'm in charge of the retail and residential structure. I wanted to give a quick overview of my design. I am designing for 12,000 square feet of retail space located in the front of the building and 24,000 square feet of residential space located in the 2 corridors in the back. The design is going to be complete with 2,000 square feet of covered outdoor space. There's going to be a 1-story steel structure located in the northwest corner of Eastgate. Back in the fall, I presented the structural layout as presented here in the middle. Using this layout, I was able to built a model in RISA floor to aid in my design process. I'm using a 22 gauge metal deck, which is also the standard deck as specified by RISA. The deck has a max span of 7 feet and it's going to be continuous over the whole floor plane, therefore making the unbraced length of the roof members 0 feet. RISA also adds a 1 foot of overhang, which is important to note when designing for the exterior members. At this point, I'm designing for the vertical loads. Here the most prominent is the snow load. Additionally, there's also going to be dead loads from member self-weight. And I've also added typical roof elements such as waterproofing, insulation, suspended steel channel, and ceiling tile, the weights of which are specified by the ASCE 7. The loads are subject to change as we go along. The loads are minor and don't have a huge impact on the overall loading. Additionally, we also factor the load using load combination 3 as specified by the ASCE 7. Running the model in RISA, we get the following layout as seen here. It's not too different from the previous layout. RISA is able to go in and take into account the maximum span of 7 feet for the metal deck and go in and design the beam spacing accordingly. And if we zoom in, we can also see that RISA adds or selects the structural members for us. We of course want to check that RISA adds members that can actually carry the loading. Where RISA is a good tool to use is that we only need to check a couple of the members throughout the structure to make sure that RISA is running the calculations right. But RISA actually goes in and selects every member for us, making it an easier design process. For the next steps, now that I've looked at the vertical loading, the next step is to go in and look at the lateral loads. This analysis is going to be done in RISA 3D, where we're going to start to design the beams, or the columns, as well as the bracing for lateral stability. Once the designs of these are known, we can start to look at the connections that are going to bind everything together. Another next step is to design the concrete floor slab. Design of the foundation is not within the scope, and the concrete floor slab is to be poured directly onto the soil. But to account for erosion, we're going to design it to have a maximum span of up to 3 feet. Another thing I haven't touched on yet is the covered outdoor space. It's going to be located in the center of the structure, and it's going to be a patio made out of timber. It's going to have the same metal deck as the rest of the structure, as well as the applied loading from the snow and the waterproofing, but will not have any of the other typical roof elements. I'm not too worried about some of the lateral loads, as it is very sheltered within the structure. My main concern is with an uplifting effect from the wind. And if this is going to present itself as an issue, I'm planning to anchor the patio to the main structure. I'm planning to have these last design elements done within the next 1 to 2 weeks. And now I'm going to pass it over to John.
As the water resources engineer, the objective of my design is to design a system that will capture and treat the first 1 inch of runoff on the area, as well as control flooding over the entire area for the 50-year to the 100-year design storm. On this slide, you can see the overview of my design. So the area in black represents the impervious area being introduced by my colleagues. Over here, this is where the majority of the stormwater runoff will occur. As you can see right here is my integrated rain garden, which will treat the water directly as it lands on top of this building. I also added a infiltration basin or infiltration trench in between the roadway and the parking lot. And then I have vegetated swales, which will transport the rest of the runoff to systems in the east. To date, I have completed all 3 designs for my rain gardens, which are shown in green, as well as the vegetated swales shown in yellow, and the culvert in blue. On this slide, you can see the design of my rain gardens. So this diagram on the right, this shows the general layout that all of my rain gardens will follow, but all the rain gardens will have different bioretention media depths as well as anoxic depths. So like I said, my targeted pollutant for my scope is nitrogen, and in stormwater, nitrogen typically is found as dissolved nitrogen, which is not removed by standard rain gardens. Because of this, I modified the outflow to have this bent elbow, which will retain stormwater in this lower part of the rain garden for extended periods of time without oxygen, and this will allow the denitrification process to be completed. In my bioretention media, I've also added a carbon source in the form of shredded newspaper, which will also help facilitate this process. Like I said, with the integrated rain garden, this is the one that is fit into the courtyard of our structural 1 engineer. It has a water depth of 0.5 feet, a mulch depth of 0.25 feet, a bioretention media depth 4.5, and a drainage layer of 0.5. So a total depth of 5.75 feet. It also stores approximately 5,250 cubic feet of water in that anoxic zone, which once the water is in the anoxic zone, it will either infiltrate through the groundwater or the ground below it, or complete the denitrification process and then therefore remove the nitrogen. Similarly, these are the designs of my northeast and southeast rain garden. The northeast is going to be the smallest one because it is only receiving runoff from the north side of the road. It isn't seeing any of the runoff from the buildings or the parking lot. That's where the southeast one comes in. This is going to be the largest one since it's seeing the majority of the runoff over the entire site. So yeah, you can also see the differences in some of the depths that are changing up slightly. Here are the dimensions of my vegetated swales. These are trapezoidal channels. Similarly, the north swale is only seeing the north side of the road, so it's seeing very little flow compared to the south swale, which is dealing with the runoff from the entire site, essentially, minus the north side of the road. Then here I have a given water depth, and this is correlated to the maximum flow rate computed with Manning's equation. And as you can see, the maximum flow rate at this given water depth is greater than the design flow rate, which means that this channel will pass the flow. Here you can see my culvert. I decided on a 2-foot diameter, 70-foot long concrete culvert. It has a design flow of 21 cubic feet per second. And this diagram to the right is made using HY8, just seeing how this culvert would operate in the real world. And as you can see, it's passing the flow successfully without flooding the road on top, so it's satisfactory. For my future work, I will need to finalize the designs of my dry detention basin as well as the infiltration trench. I will need to complete CAD drawings for all of my designs, and once I know the final design, I will estimate my construction costs. And from here, I will pass it over to our second structural engineer, Aubrey.
Thank you, John. So as the second structural engineer, I have a couple of responsibilities that I will recap real quick. One of them is to build a 25,000 square foot academic building, and that building will have 1,000 square feet reserved for indoor multi-use area. This area will be at the front of the building, so it'll open up into a lobby, and then the surrounding area will be classrooms and laboratories. And as previously discussed, I have gone through multiple alternatives and analyzed these alternatives with many parameters, and I'm still confident that a 1-story steel structure will best fit this design. And it is located where the red rectangle is on the screen. As for my loading, this is what I put into RISA 4. So these are not lateral loads yet, that will go into RISA 3D. I use the beam self-weight, which varies depending on the member being referenced, and a 22 galvanized steel deck with a 1.9 PSF weight. And then for a live load, I used a roof load and a snow load. However, the snow load did control with 45 PSF. All of these loads are from both the ASCE hazard tool, ASCE 716, and LRFD. As for my roof and floor plan, I used a 12-inch overhang and the deck that I previously said. And the deck will be 10 by 25 feet. And then here you can see my spacing of my beams, girders, and columns. My columns will be 12 feet tall, so my stories will each have a height of 12, and my beams will be 25 feet spaced at 10 feet, while my girders will be 40 feet spaced at 25 feet. And then this is what RISA gave me for the results, and I did do hand calculations to check them, which can be referenced in the appendix of my most recent report. The columns are probably going to change when the lateral loading is applied in RISA 3D. This is just a beginning part, and they're all subject to change based on the lateral loading, but I'm expecting the columns to change the most. And as for future work, I will be designing my concrete floor slab, and as previously mentioned, my RISA 3D, which will be the lateral loading, the bracing, and the columns, and basically everything except for the floor and roof plan. This will also include connections and concluding with a finished design. This design will include a finalized cost estimate, as the one I have right now is just by RS mean square foot estimator. So it's more of an average of what it usually is, but this will be specific to my project. Speaking of cost estimates, we have our construction cost estimate at $20.8 million. This will not include water resources, as we need the finalized design to include it. It includes transportation, both structural buildings, and a demolition cost of a couple of the houses we needed to remove, and a 15% contingency. These were all calculated using NDOT price summary and RS mean square foot estimator. As for our total design cost, we have a total design cost of $86,000. Again, this is a 15% contingency. We used the position classification, hourly wage, and hours to decide this design cost. And I have a breakdown of how we decided the hours here. We broke down each aspect of what we will have to do in the future, which includes things like CAD design, floor slab design, and more, as we all had mentioned. And estimated how many hours we will be spending on each of them. As you can see at the bottom, we all have a cost estimate, so we will be having a more accurate cost estimate specific to our presentation and project next presentation on April 30th. With that, thank you. Does anyone have any questions?
That number 45 for the snow loading seems to bother me. So can you shed some light? Is it like snow drifting in here, or is it the uniform snow loading that the computer is spitting out for you, the RISA?
Yeah, what we did was we used ASCE hazard tool to get kind of like the drifting snow load, I guess you could say. And then we used an equation in ASCE 716 to calculate the snow load. I can show you the equation and all the references.
What's a uniform snow load compared to the 45 pounds per square foot in here as the drifting in here? But I'll tell you what, I designed buildings before, and I used the 20 pounds. So
Yeah.
you want to justify to me why you are using 45?
We used 45 because that was what our hazard tool gave us. We could,
Can you trust that tool?
yes.
Because the same, like Emil mentioned, like the roof at 22 gauge in here as the default value in RISA. You just accepted the value?
Yeah, I mean, trust it. If it presents itself as an issue, it's something I can look into changing. But
We did check all of our results with hand calculations.
Yeah.
And so those are all in our appendix of the last report.
And Kanzi, I saw when Jolie presented her like the horizontal curves, it was 750, the radius.
Mm-hmm.
Yours is 500?
Yes, so the minimum is actually 300, but to design of the people's eye, that it would be easier for 500 for my alignment. Because her alignment is also connected to, we're gonna have to keep with that.
Boilermaker.
Yeah, Boilermaker Court, and mine is connected south of that. So Boilermaker Court is up here more, and mine's down south of Boilermaker Court.
Okay.
So that would also include why mine is also a little different. Because when I did my level of service, I only needed a one-way stop, and she did a two-way stop or four-way stop. So I only have one stop sign going out and to be on the main road.
And now maybe ask you the same question. Did you use the help of like InfraWorks or like Civil 3D into deciding?
Yes, this is actually all designed on, and as you can see, my alignment was also designed on Civil 3D. And that's how I came up with this. So this is along the existing, and that's how I came up with these percentages because of construction costs and whatnot. It would be easier for them to try and build more on the existing alignment rather than creating a whole new alignment, except besides the culvert that we'll be placing.
Did you need a surface model to establish those alignments?
Yes. Yeah. Because that will be like on the, yeah. Any other questions? Okay.
A question for John. Does your, or do your rain gardens or your other stormwater management practices, like, do they have pre-treatment? I didn't see pre-treatment on your.
So my rain gardens over here, they flow through vegetated swales beforehand.
Mhm.
And then I also have, once the rain enters the rain garden from the roof, then there's also a dry well that will slow down the flow and also hopefully act as some sort of pre-treatment. I also have pre-treatment up here before the infiltration trenches.
So what's the pre-treatment there?
So just vegetation through the vegetated swales. It should be flowing like slow enough to settle out some of the solids and help prevent any sort of clogging.
Okay, so when the water comes off the roof of that rain garden, it's going into a dry well and then overflowing into the rain garden?
Yeah.
Oh, okay, thanks.
Anything else? Mr. Chickle?
I'm a transportation guy, so I'll ask
Okay.
John some further questions. Because I don't understand what anoxic is. Could you tell me what the definition and what that zone would be doing for me?
Yeah, so this zone, basically it just means that in this zone, there's extremely low oxygen levels. So that will just, I'm not completely familiar with the chemistry of denitrification, but I know in order to have denitrification occur, you need to deprive the water of oxygen. And also adding a carbon source in there, but yeah, the anoxic zone, yeah, just means without oxygen.
So two questions. So one is transportation and water related. So on the culvert side, you're dropping the grade down to the culvert. So where's the culvert located to the road right now? Like how far is it down?
So the original slope right here, there's actually nothing right now, it's just like a big dwell of land. So, and like there's a stream down there. So right now, I think the slope was like 30%, which is not applicable for this. So that's why we decided to place the culvert, and then there's a standard for how much road needs to be placed over the culvert. So we'll do the dimensions and then figure out from there how much the road will go over.
And I just finished dimensioning my culvert, so I found that it was 2 feet, so it's just gonna be at the very bottom right there, so it's.
Right. But how far down from the road?
I will need to double check, but I believe it's about like 20 feet, 25 feet, something like that.
And how far does the road, I'm thinking, is it viable to just run the road straight and put more fill in? Or
Yeah, that's probably what we're gonna do. So we need a little bit of a thing just because of that. There would be a lot of fill and it's easier to place on top. But right here, you can't really see it. But it like connects to the existing road. I don't know if you can see like that little bit. So that is the existing road at Silhavy that it will connect to, which is a little bit like below what our existing pavement was here. So it would need some slope just because it does like dwell down to Silhavy Road.
okay. Thank you.
Mhm.
And then the other question, Mr. John, so the shredded newspaper, explain how that works, especially long-term.
So, again, I'm not like very familiar with the chemistry, but this was just following a study that was looking into nitrogen removal in rain gardens. So they tested multiple different additives to the bioretention media, just different types of carbon sources, and then after that would just analyze and see how well it did in nitrogen removal. And in that study, shredded newspaper was the best alternative. So that's why I chose that.
So am I visioning this right, that someone's gonna be out there from time to time just tossing shredded newspaper?
It would probably be a little more in detail than that.
Effectively, so it'd like be like recharged or something?
Yeah, there'd be some maintenance involved. We'd probably have to dig up some of the bioretention media, then mix it, and, just try to get it back to the same condition it started in. But,
So why newspapers? So the paper is the carbon source, correct?
Yeah.
How about the ink? Is that gonna be like a toxic material being added to?
I would assume not. You'd have to ask the newspaper people.
Any more questions?
Well, just one. Go back to that HY8 schematic. Well, looking at the water levels in here, don't you think this is way oversized, the culvert?
It could be. I could size it down. It was only a 2 feet diameter, so I could size it down. The reason why it's so there's so much space there is because we're in the bottom of a ditch. So it's like they would take a lot of water to fill up this entire area. So I potentially could size it down a little bit more, but it's I don't know. I can look at it.
Does Valparaiso have a minimum
It's
diameter?
a minimum of 1 foot,
Yeah,
so
okay.
I just had to go a little bit above that. So that way it doesn't, the water doesn't rise up as much. Anything else?
Thank you.